Hello, everybody, and welcome back to BioSC 140 Human Physiology. This video is going to cover S4P1 Part 2 of the renal physiology lecture. So, you're in for a treat today. Get it? Okay. Urinary excretion depends on filtration, reabsorption, and secretion. So, filtration. What's filtration? Reabsorption. What's reabsorption? Secretion. What's secretion? So what eventually becomes urine is based off these three processes. So filtration is fluid leaking out of the glomerular capillary into Bowman's capsule. That's filtration. Reabsorption is when fluid goes from the renal tubules back into the peritubular capillaries. And secretion is when substances go from the peritubular capillaries into the renal tubule system. So reabsorption mainly happens in the PCT, proximal convoluted tube. It's water, glucose, ions, amino acids, vitamins, bicarbonate, BUN, blood urea, nitrogen. In order to be reabsorbed, you have to be filtered first. So all these things, water, glucose, ions, amino acids, vitamins, bicarbonates, BUN, it all gets filtered out through the glomerulus and then completely or partially reabsorbed. Do red blood cells get filtered out of the glomerulus? No, they stay in the bloodstream. Do large proteins get filtered out? No, large proteins stay in the bloodstream. Secretion mainly happens in the distal convoluted tube, DCT. We get hydrogen ions, xenobiotics like penicillin. So those are foreign biomolecules. Creatinine, ammonia, PAH, various wastes. Glomerular filtration rate is dictated by opposing forces. So these are the same basic forces that we see in normal systemic capillaries. Some of the names have been changed. But they're the same basic forces. You have the hydrostatic pressures in the glomerulus pushing out. You have the hydrostatic pressure in the nephritic tubules and Bowman's capsule pushing back in. You have the oncotic pressure of the blood, of plasma, pulling things back into the glomerulus. You need the oncotic pressure of the tubules pulling things out of the glomerulus. And it's the balance of those that gives us our net filtration pressure. So net filtration pressure is the pressure that drives filtration. Net filtration pressure is the pressure that drives filtration. Net filtration pressure, if it's greater than 0, we're going to have filtration. So your body needs to maintain the proper balance, just like with the systemic just like with other normal capillaries. Our body needs to maintain a balance between the forces out of the glomerulus and the forces into the glomerulus. The combination of those forces is your net filtration pressure. So what is ultrafiltrate? What is ultrafiltrate? Ultrafiltrate is the name of the stuff that gets filtered into the capsule. So part of your plasma is going to leak out of the glomerulus, glomerular capillaries, into your Bowman's capsule. When it's in your Bowman's capsule, once it gets in there, it's called ultrafiltrate. So about 180 liters a day gets filtered into your nephrons. That's a lot. 92-liter soda bottles, 180 liters a day gets filtered into your nephrons. That's 125 milliliters per minute. Those normal, like standard size plastic water bottles? It's like they're what, like 500 milliliters? That's like one of those every 4 minutes. You filter your entire plasma volume, about 3 liters, 2.5 times an hour. All of your plasma gets filtered out 2.5 times an hour. Yet, you only excrete about 1.5 liters a day as urine. Now, this does vary, but about 1 milliliter per minute is a good average urine production rate. Minimum, you need about 0.5 liters a day to secrete all the waste that a person produces. Reabsorption is energy intensive. It takes a lot of energy to reabsorb everything back into our bodies. And kidneys receive about 20 to 25% of cardiac output at rest, 1 liter a minute. 20 to 25% of all the blood that your heart pumps goes to your kidneys. That's incredible. At rest. That's incredible. So, this shape that we've seen so far, when we have talked about the anatomy, the different parts of the nephron, isn't exactly correct anatomically. We've kind of unfolded it so that we can show the different parts. In reality, it kind of folds back on itself, and this form and function is going to really go hand in hand. So right here we have our afferent arteriole. This is a good depiction. We have our afferent arteriole, our glomerulus, our efferent arteriole. We have our Bowman's capsule, proximal convoluted tube, loop of Henle, ascending and descending. And what you'll notice is that it loops back around right by the glomerulus. It's not kind of unfolded like this. It's got to loop it back around. It's looped back around so that it crosses really close. And there's an important reason for this. The juxtaglomerular apparatus contains specialized sensory cells. So juxtaglomerular next to the glomerulus, break the word down, makes sense. The juxtaglomerular cells, these cells right in here, they're also called JG cells. You'll hear me call them JG cells. You might see them on the test like that, or juxtaglomerular. They are smooth muscle cells on the afferent arteriole, so these pink ones. Smooth muscle cells on the afferent arteriole, and they are mechanoreceptors. They detect stretch, and stretch is, it's caused by blood pressure. So they sense blood pressure by sensing stretch in the afferent arteriole. And they will secrete renin, which is a hormone, which we'll talk about later on in this lecture, which helps regulate sodium chloride salt levels and salt and water balance. Remember, blood volume is the long-term control of blood pressure. And so when these JG cells, they detect blood pressure and they secrete renin to help stabilize it long term. The macula densa is another set of these sensory cells right in this area. So we have this macula densa, it's modified tubule epithelium. So the macula densa are this dark blue purplish color right here. Modified tubule epithelium. And the macula densa contains osmoreceptors, chemoreceptors, and mechanoreceptors. And these macula densa cells, they're in this section of tubule, and this section of tubule loops back around by the glomerulus so that they can communicate. We have some local communication in this area. When the blood flows in, JG cells sense pressure. JG cells can cause change. Macula densa is near the end of the tubule system. Macula densa senses changes they can send messages to the beginning to help regulate what's going on in this process. See how that works out? JG cells kind of monitor what's going in, can affect change. Macula densa cells kind of monitor the end and can affect change at the front. So here it is depicted another way. So we have our JG cells, these smooth muscle cells in the afferent arteriole. Right here we have our macula densa cells, or macula densa cells. Tubuloglomerular feedback. Tubuloglomerular feedback. Fluid flow through the tubule influences GFR, or GFR is glomerular filtration rate. So glomerular filtration rate is subject to autoregulation. So I want to point something out. We have net filtration pressure, NFP. That's referring to the forces. Net filtration pressure is referring to the forces that promote filtration. GFR is glomerular filtration rate. It's the rate at which fluid is moving. So they're similar. Net filtration pressure helps dictate glomerular filtration rate, but they are slightly different. So tubuloglomerular feedback, fluid flow through the tubule influences GFR. An increase, so if there's an increase, like a too much flow within the tubule system, the macula densa cells detect it. The macula densa cells will tell the JG cells. The JG cells in the afferent arteriole can constrict, which will decrease blood flow to the glomerulus, decrease the hydrostatic pressure within the glomerulus, which will decrease glomerular filtration rate. So once again, we have the JG cells at the front, which can detect stretch, which help regulate, GFR on the way in. And we have macula densa cells, which detect stuff in the tubes, which can talk to the JG cells. We kind of have sensors at the beginning and sensors at the end. They can help regulate GFR. So right here, net filtration pressure is determined by forces that push and pull. So glomerular filtration rate is dictated by opposing forces. So net filtration pressure refers to pressure. Glomerular filtration rate refers to the rate at which ultrafiltrate is produced. Yes, they are related. Yes, they are different. NFP is determined by forces that push and pull. So NFP, it's the same forces as Starling forces. It's the same forces at a normal, quote unquote, normal capillary. Just they have different names. So the forces out, the forces that are promoting filtration, we have glomerular hydrostatic pressure. So the hydrostatic pressure, the blood pressure within the glomerulus. We have capsular osmotic pressure. Capsular osmotic pressure. So the pressure that dissolved proteins are pulling fluid that way. No proteins get out into the capsule, so there's no proteins pulling fluid into the capsule. Reabsorption forces. We have CHP, capsular hydrostatic pressure. That's the hydrostatic pressure within the capsule. And then we have glomerular osmotic pressure. This is due to plasma proteins, albumins, things like that. Dissolved proteins pulling fluid and keeping fluid in the glomerulus. So net filtration pressure is equal to forces out minus forces in. Net filtration pressure is equal to glomerular hydrostatic pressure plus capsular osmotic pressure, the out forces, minus capsular hydrostatic pressure plus glomerular osmotic pressure. If NFP is positive, then we get filtration. So glomerular filtration rate, GFR, is the volume of filtrate formed per minute. So it's how much ultrafiltrate gets formed per minute. It's related to net filtration pressure, as net filtration pressure is going to influence it, but it can also be affected by the surface area. So How many nephrons does the person have? Or membrane permeability. I had a dog, Corey, little Corey, and she long story, but her visceral layer of her Bowman's capsule was damaged, and it became permeable to proteins and other things. So her membrane permeability increased significantly because of her disease state. And so net filtration pressure was the same, but GFR went up. So it's not just NFP that determines GFR, it's also surface area and membrane permeability. Little Corey, her membrane permeability went up. All right, so capillary pressure is regulated locally by afferent and efferent arterioles. So your body wants to regulate GFR. It wants to regulate how much fluid is becoming ultrafiltrate. Your body can change and alter and regulate this. And it does so locally by the afferent and efferent arterioles. Afferent and efferent arterioles. Remember, arterioles, remember back to test 3, arterioles are muscular. There's a lot of muscle in arterioles. They can constrict and relax. They can change their radius, which changes their resistance, which changes blood flow. So let's say you want to decrease the pressure in the glomerulus and decrease GFR. Well, constrict the afferent arteriole. This will increase the resistance, which will decrease pressure in the glomerulus, which will decrease GFR. Let's say you want to increase GFR. Well, you dilate the afferent arteriole so that less resistance, more blood flows in, and you constrict the efferent arteriole, causing blood to back up behind it, which increases the hydrostatic pressure in this area, which increases glomerular filtration rate. So the local blood pressure in the glomerulus can be regulated via constriction and relaxation of the afferent and efferent arterioles. You can regulate your GFR via the afferent and efferent arterioles. In fact, glomerular filtration rate is stable over a wide range of blood pressures. Your body can maintain a very stable GFR within a very wide range. Yes, numbers will vary specifically from person to person and also from source to source. As you can see on this slide, it says 80 to 180 on the picture, but down here it says 50 to 150. Expect a question on this on the exam. Nudge, nudge, wink, wink, hint, hint. But I'll use numbers that work for both of these ranges. I understand, different sources, you'll get different information, but the main point is that blood pressure stays similar. Not blood pressure. Glomerular filtration rate, your body can maintain a stable GFR, even if there's a change in your map. So this is how a question might look, and this will be good practice. See if you get this concept. So-and-so, Dan has a glomerular filtration rate of 180 liters a day. Dan's MAP is 100. At 100 MAP, his glomerular filtration rate is 180 liters a day. If Dan's MAP increases to 120, what will happen to his glomerular filtration rate? So my MAP at 100, glomerular filtration rate is 180 liters a day. If my MAP goes up to 120, what's going to happen to my glomerular filtration rate? Well, my body is able to maintain stable GFR within that blood pressure range. So my GFR will still be 180. Now what's going to happen if my blood pressure goes up to 250? If my MAP goes up to 250, I'll have bigger problems that I'll need to deal with. But if my MAP's at 250, yes, then my body cannot regulate GFR, and I'll have an increase in GFR because it's way outside this range of 50 to 150 or 180 to 80. What if my MAP drops to 30? If my MAP drops to 30, it will decrease my GFR. But within this range, GFR is not going to change. All right, let's take a closer look at these forces that promote filtration. So we have GHP, or glomerular hydrostatic pressure. That's your blood pressure within the glomerulus. What can change this? Well, extreme hyper or hypotension. That's what we're talking about up here. If normally our glomeruli, or afferent arterial, are able to maintain a stable kind of pressure in this area, they can dilate or constrict and work for a stable GFR. But sometimes, like if MAP drops to 30 or if MAP increases to 250, we're not going to be able to maintain a stable GHP force. COP, capsular osmotic pressure. So capsular osmotic pressure is the osmotic pressure within the tubule system that's pulling fluid into the tubules. Normally, there's no proteins in our tubules, so this force is next to zero, basically. Well, think about my dog, Corey. Corey had damage to her visceral layer, to her podocytes, and proteins were leaking into her tubule system. If proteins are able to leak past the filter and get into your tubule system, they will pull more fluid into your nephrons, throwing off your GFR. Hypertension, extreme hypertension, can also push proteins through the filter. Now that's really, really high hypertension. That can happen. CHP, capsular hydrostatic pressure. So this is the hydrostatic pressure of the tubule system. Let's say you get a kidney stone and it blocks the tubule system. Fluid keeps flowing in, but it's coming into this rock, this thing that's blocking it. That can increase CHP, capsular hydrostatic pressure, which will decrease GFR. Glomerular osmotic pressure is going to be the number of proteins and dissolved stuff in our plasma. Well, if you're malnourished, if you remember kwashiorkor, if you're malnourished, you don't have enough protein in your plasma, it can throw off your GFR. It can throw off your GOP, which throws off your GFR. Liver damage, so you have fewer blood proteins. So there's a wide range of pathologies that can alter these forces and have an ultimate effect on kidney function. Glomerular filtration rate is regulated by intrinsic and extrinsic mechanisms. So our intrinsic mechanisms are going to be the renal autoregulation. The kidney regulates its own blood flow, typically via arterial diameter. So this is going to be your autoregulation. This is going to be our JG cells and our macula densa. Extrinsically, hormones can affect GFR and kidney function, and the autonomic nervous system can too. So intrinsic is going to be our myogenic mechanisms. Arterioles alter their own diameter. That's something we covered in lecture exam 3. So arterioles all regulating their own diameter. And then we also have the tubuloglomerular feedback. So fluid flow through the macula densa have an effect on the GFR. So JG cells detecting changes in pressure and acting accordingly. Macula densa detecting change in osmolarity, in pressure, in different chemicals, and talking to the JG cells to influence GFR. Intrinsic autoregulation. Right here's our myogenic autoregulation. So arterioles change in diameter in response to pressure. There's an increase in blood pressure. There's an increase in stretch, which causes an increase in constriction. which counteracts that increase in pressure. Flow is maintained. Glomerular hydrostatic pressure is maintained. Macula densa. So when fluid flows through the, fluid flow through tubule influences GFR. If we have a decrease in flow, we have an increase in osmolarity. The macula densa tells the afferent arterioles to dilate, which will increase blood flow to the glomerulus and increase GFR. If there's a lot of flow in the macula densa and low osmolarity, macula densa will tell the JG cells, the afferent arteriole, to constrict, which will decrease blood flow to the glomerulus, which will decrease GFR. Extrinsically, we've got the autonomic nervous system. So the autonomic nervous system will talk to these afferent and efferent arterioles and have an effect on their diameter. Remember this, the sympathetic nervous system goes to vessels and to our kidneys. Sympathetic system goes to vessels and to our kidneys. The kidney is exclusively innervated by the sympathetic branch. So sympathetic stimulation, arterial constriction. The afferent has more alpha-1 receptors, which causes more constriction. So alpha-1 receptors get stimulated on the afferent arteriole, which causes constriction. They can also stimulate the JG cells to release renin. And renin activates the angiotensin, renin, aldosterone system, which we're going to get into not in this part, but really soon we're going to get into renin and all of renin's friends. So don't worry, that's coming up. All right. And then hormones. Glomerular filtration rate is regulated by intrinsic and extrinsic mechanisms, autonomic nervous system, and also hormones. Again, that's going to come up soon. It's going to come next, actually. I'm actually going to end this part right here, and we will get into the hormones in part 3. All right, everyone. As always, if there's anything I can do for you, let me know, and I will see you in the next video.